In this series of NMR lectures, all of you have been acquainted now to understand the fact that the way to get a signal is by applying a perturbation pulse followed by an acquisition of the time domain signal, which is called the free induction decay. Although we keep drawing a continuous function as the signal during the acquisition period, in reality this gets digitized in the NMR hardware. This is performed by the device called analog to digital converter. What this essentially does is that instead of taking a continuous signal, it ends up sampling a few points that are dictated by the Nyquist sampling theorem. Briefly, the Nyquist sampling theorem says that if you are trying to capture motion that has a frequency nu, you should at least sample data at twice the frequency so as to ensure you get the real frequency nu. You might have observed this at times where when you look up at your fan when the light is a little dim, you end up seeing the fan rotating in the opposite direction, although you definitely know rotating in a certain direction. So the Nyquist sampling therefore dictates that if you have a certain spectral width, where SW is going to be called the spectral width, traditionally this is also called the sweep width. Since we don't sweep anything anymore, we would refer to SW as spectral width. The moment you set a spectral width SW, the dwell time is going to be dictated by the spectral width, where the dwell time is going to be given as 1 over spectral width. But the point that you must remember is that since you have to at least sample twice as fast, you're going to have 2 times spectral width there. So the spectral width is also the window in which you would like to measure the signals that are present. So for instance, let's take the simplest example of a proton NMR spectrum. And for the sake of simplicity, we can imagine that we are trying to get signals between 0 and 10 ppm. And therefore, by default, you're going to keep the carrier at 5 ppm. And for this example, let's assume we are collecting the data at 500 megahertz. So therefore, the spectral width, which is 10 ppm, in hertz is going to be given by 10 times 500. This is going to be 5000 hertz, or in other words 5 kilohertz. So therefore, you know that the 0 ppm here corresponds to 500 megahertz. On the other hand, if you set the carrier at 5 ppm, it indicates that in this example, omega RF is set to 500 megahertz plus 5 times ppm, which is 5 times 500. This will nothing but be 500.25 megahertz. So your omega RF in this example, as we are taking, is going to be at 500.25 megahertz. And since your spectral width is 5000 hertz, you have 5000 divided by 2, meaning that this entire range is 5000 hertz, and therefore you're going to be spanning 500.50 megahertz until 500.00 megahertz. So now, having done this, the step that we need to understand, what will be the dwell time. It's going to be given by 1 by 10,000 hertz because you want 5000 hertz to be sampled. So this ends up being 100 microseconds. Now that you have 100 microseconds, and let's go back to the signal that we were trying to acquire. So we said that duration between the points, each of the points is going to be 100 microseconds. And what is this total acquisition time going to be decided upon? In order to do this, I'm going to remind you of the basics that we had learned earlier, meaning that following pulse, the total transverse magnetization as a function of time, basically the time domain signal, by the Bloch equations. Under this condition, let's take for an example, we are going to end up applying a 90-degree excitation pulse from equilibrium. So therefore, your m plus of naught is going to be m naught. And for all practical purposes, we can take m plus of t over m naught so that we normalize over m naught. It's going to be given by exp I omega I t times exp minus r2t. For the signal to decay to 5% of the original signal, meaning that going from 100% to 5%, let's ask how long will it take. So therefore, the LHS is going to be 0.05. And you know for a fact that the oscillations won't end up resulting in signal decay. On the other hand, the relaxation part would. So therefore, if you solve this equation, you would end up observing that the time required for the signal to go from 100% to 5% is to the tune of 3 times T2. Writing T2 star here because if there are inhomogeneities that come from the magnet, you would actually have shorter T2 times. This also is one of the main reasons why people expect you to make sure the shimming process, which ensures the homogeneity around the sample, is done prior to your data acquisition. So now, continuing with the example that we are trying to think, let's assume that the T2 star that we are talking about for a small molecule is 500 milliseconds. So therefore, your total acquisition time, people would end up setting to 1.5 seconds. And we just learned that the dwell time for the 10 ppm spectral width on a 500 megahertz works out to be 100 microseconds. So immediately, if you end up calculating what are the total number of real points, in this case, it's going to be given by the total time divided by the dwell time. And the reason why we end up doing NP by 2 is because we are just trying to talk about real points here. So total number of points NP is going to be given by NP by 2 real points and NP by 2 imaginary points. So we try to mean NP for the total number of complex points that we are trying to record. So this indicates the total number of points gets immediately decided once you have a spectral width and your total acquisition time. In an actual NMR spectrometer, people would end up either choosing the spectral width and the total number of points, or spectral width and the total acquisition time. And if you're able to realize, the moment you choose the spectral width and the total number of points, your acquisition time gets decided. On the other hand, if you end up choosing your spectral width and the acquisition time, then your total number of points get decided in such a case. So there are a few more parameters that we would like to take a look at. So the first question that we have is that what happens if you acquire forever, meaning that if you set acquisition time to infinity? What does this indicate? After your oscillation has died down, what if I continue to record? The problem will be that after your FID has died, you're going to be picking up something called noise. And by discrete Fourier transformation, the total number of points in the time domain will be equivalent to the total number of points in the frequency domain. So essentially the resolution would increase, meaning that you'll have more number of points that defines the spectral width that you're trying to have. But the unfortunate thing would be the noise from the time domain would translate to noise in the frequency domain. So let's say that this is the noise if you end up just acquiring this amount of points. The moment you go to more number of points, the noise in the spectrum would significantly increase. And this would therefore result in reduction of the signal to noise ratio. However, the total resolution is going to be given by 1 over acquisition time. Resolution is nothing but the total number of points that you have per hertz. You are able to understand here, as you keep increasing acquisition time, the resolution increases. However, comes at the cost of noise that might end up coming in the spectrum. So this is always a compromise between these two parameters of what will be the resolution that you would end up getting versus the sensitivity of the given experiment. Having gone through these many points, there are only a few subtle features that are left out to be understood in the pulse program. So let's go back to our excitation pulse followed by the acquisition of free induction decay. So we said it's going to be given by a certain flip angle at a given phase, and you end up acquiring the signal. And we just ended up discussing most part of the data acquisition, and the perturbation has been done in great detail in the classical portion and also in the quantum mechanical portion. The yet another aspect that one has to learn from here is this important delay called recycle delay. In a few places, this is also referred to as the relaxation delay. As you might remember, the rate at which the transverse signal decays is going to be given by the characteristic T2 constant. The time required to recover the signal or the magnetization following a perturbation is going to be given by the T1 time constant. Going back to the block equations, if you look at the fact Following a 90-degree excitation from equilibrium, you would end up having zero longitudinal magnetization. The time taken for the magnetization to recover back to the longitudinal axis to about 99% is going to be given by 5 times T1. I urge you guys to solve the block equation so as to understand what's going on here. And from here, what you are able to understand that T1 times, which are characteristically longer, for this example, we can take this to be 1 second. We assumed T2 time as 500 milliseconds and T1 as 1 second. What you are able to realize is that the total acquisition time, you're going to set it up to 1.5 seconds. On the other hand, the D1 time is going to be set to something like 5 seconds. You are able to understand that your pulse that you ended up applying is going to be for a short duration. Let's assume a 10 microsecond pulse for a 90-degree excitation of the proton channel. The important thing that one notes here already is that most of the time, that is for about 6.5 seconds for a given scan, you are sitting idle. Interestingly, there have been fast pulsing methods that people have realized that instead of setting the alpha to 90 degrees, if you set the alpha to 30 degrees or a flip angle that's less than 90 degrees, you can actually reduce the D1 time in order to ensure you can pulse faster. I'd like to remind you guys that the acquisition time is also the duration in which the spins would recover. So in reality, although we said this has to be 5 seconds, a smart person would set the relaxation delay for this experiment as 3.5 seconds because the sum of 3.5 and 1.5 seconds would be 5 seconds, which would be 5 times T2 for this example. Without going into further details here, I'm stopping it right there. One is able to understand that if you're still implementing a certain flip angle pulse, the D1 cannot be as long as 3.5 seconds because you end up wasting a lot of time, which could be used towards measurements. So therefore, what people end up doing is to keep D1 somewhere in the ballpark range of 1 to 2 seconds. However, what they end up doing is to do something called dummy scans. These are also called as steady state scans. The Bruker terminology, the dummy scans or the steady state scans is given the variable ds. What this essentially achieves is that it already pulses a few times before recording signal in order to ensure that the magnetization that is along Z has reached a certain steady state. This is important because most often NMR spectroscopists would like to get proton 1D NMR spectrum which are integratable because one ends up relating it to concentration of the spins that are present. So the purpose of these dummy scans is to ensure that a certain steady state is reached for all the spins so that following acquisition of the NMR spectrum, one can integrate and get meaningful results. One other important point that one has to be careful about is that if you do not want to do steady state type of acquisition, the best way of getting very reliable integrals in an NMR experiment is to set a very long relaxation delay and also ensure that the acquisition time is appropriately set so as to get a very good signal to noise ratio by repeating the same experiment again and again. This is a very common thing that is done in every NMR experiment, and this is called signal averaging. What does signal averaging achieve is that if you acquire a single scan experiment, what will end up happening is that you might not be happy with the signal to noise that you achieved. So therefore, what people generally do is to repeat the same experiment over and over again by repeating the number of scans. So when you keep repeating the same scan over and over again, the logic works in the fact that noise is sporadic while your signal is periodic. So therefore, when you average, the signal will keep coming in the same place while your noise will keep coming in different ways. So therefore, noise ends up destructively interfering with one another, where noise scales proportional to square root of the number of scans, largely because it has a destructive interference, while signal ends up scaling with the number of scans. So therefore, your signal to noise ratio ends up scaling with the square root of number of scans. What does this mean? If you want to double your signal to noise ratio, then you need to increase your number of scans 4 times in order to achieve the same thing. And if I would recollect the signal to noise ratio that was introduced to you, it's directly proportional to n, gamma e, gamma d power 3 by 2, b naught power 3 by 2 times the filling factor k, the whole divided by delta nu, and then a bunch of temperature and resistance parameters, which I'm not going to be writing right now. You are able to understand that now the concentration matters a lot. If you half your concentration, you need to run the number of scans 4 times. And this matters a lot here, which is why people would never compromise on the concentration that they end up getting their NMR sample in. And as we know that NMR is an insensitive technique, this results in the fact that you would like to have high concentration and repeat your experiment several times in order to get better signal to noise ratio. I hope this entire lecture has given you an idea of different modules that are present in an NMR experiment. Namely, you understand what's a recycle delay and how following a pulse the signal is acquired in terms of Nyquist sampling. And in addition, how are these various parameters of the recycle delay, the acquisition time are set. And at the same time, you also try to understand how noise ends up playing havoc if you keep acquiring signal forever. And in addition, you also learn that dummy scans help you reach a steady state so as to ensure that the integrals work out fine. In this case that you don't want to do with a steady state, you end up having a very long D1. And the most important aspect of NMR, signal averaging, is a very important aspect in order to improve signal to noise. However, comes at the fact that if you want to double your signal to noise, you need to acquire the experiment 4 times longer.